Hello everyone, welcome to another class of fundamentals of particle and fluid solid processing. As discussed in the last class that couple of concepts on drag force and the boundary layer as well as the boundary layer separation. We have seen couple of problems to clear our this confusion or any there was any issues with the concept. So, and we will continue that in this class as well. So, if we go to our first problem here, the problem is defined as like this, that a viscous fluid is flowing over a flat plate such that the boundary layer thickness at a distance 1.3 meter from the leading edge is 12 millimeter. Assuming laminar flow, calculate the boundary layer thickness at few distances that are mentioned here, which were 0.2 meter, 2 meter and 20 meter from the leading edge. Okay. So, very simple problem. Immediately you should have in mind that how the boundary layer developed for a flat plate. Like there was some approach velocity, and then from the leading edge the boundary layer was from x is 0, if the leading edge is x is 0 to x is delta. At a certain distance the boundary layer thickness becomes delta for a certain x. So, this is the problem, the similar based on the very fundamental concept that we have to calculate now here, that what are the deltas at different x's, that is from x is equals to 0 to the downstream of the flow. So, how do we solve this problem? Okay. So, if we look at it, we know that here the boundary layer thickness is basically proportional to the distance to the power 0.5. This we have discussed in the previous class. So, again here the assumption is that assume laminar flow. For such flow condition, we know that this is the relation, that delta, the boundary layer thickness, varies proportionately with the square root of x, where x is the distance from the leading edge of the flat plate. So, which means k is a proportionality constant which should be determined at first from the given value, and here the given value is already given. So, that for 1.3 meter at a distance from the leading edge, the delta is 12 millimeter. So, here delta is 12 millimeter, x is 1.3 meter. After having the consistent units, we find the value of k, which is the proportionality constant. So, that means we can find out how delta and x varies for this particular problem. Then it is simple, we replace the value of x with those different values or the values that has been asked in the problem, that for 0.2 meter, 2 meter and 20 meter. What are the values? We replace those values here and find that delta, the boundary layer thickness, are like these values, that is 4.7 millimeter for 0.2 meter distance. When it is 2 meter distance, it is 14.8 millimeter width, the boundary layer thickness, and for 20 meter, the distance from the 20 meter, the boundary layer thickness is of 47 millimeter. So, once again here we have just played with the concept that boundary layer thickness for laminar flow varies with the square root of x, even without knowing any particular correlation. For a given value, we have at first calculated what is the proportionality constant or how it varies, the relation between delta and root over x for laminar flow, and then replacing the values of x, we have found out that what are the values of delta in these cases. Very simple problem. I hope you have understood. The second problem, if we move on to, it says that determine how far from the front edge of a flat plate the boundary layer becomes turbulent when fluid approach velocity is 1 meter per second. This is the first part. The second part is that how thick is the boundary layer at this location. That means the location where the boundary layer becomes turbulent, or the onset of turbulence occurs. From that point, what is the thickness at that point of the boundary layer? So, which means before that we can understand that till that distance from the leading edge the laminar flow exists. Now, in this case few physical properties are required. I told you earlier that such physical properties are either given or you have to find out from any textbook or any given table. So, in this case how do we do that? So, here the question is that determine at the distance where the flow or the boundary layer becomes turbulent, the flow in the boundary layer becomes turbulent. So, which means that we have to find out that what is the critical Reynolds number. Okay. Now, critical Reynolds number for such type of flow, that means when there is a flow over a flat plate, the critical Reynolds number, or we know that the transition occurs or the turbulence begins, is 5 into 10 to the power 5. Okay. And this critical Reynolds number is nothing but u, the velocity of the flow, the critical length of the flat plate from the leading edge, and the nu, which is the kinematic viscosity. These values are given, u and nu, where u here is 1 meter per second. The nu value is already given, 1.5 into the power minus 5 meter square per second. So, we find that what is the critical x that is required, or the length from the leading edge that is required to have the critical Reynolds number, which means where the turbulence begins. So, and now at this length from the leading edge, we use this Blasius relation, that again this is the relation between the thickness of the boundary layer and the Reynolds number, okay, at a certain distance from the leading edge, that is x, that is given by Blasius. So, here we get the, after replacing the value of x as x critical and Re as this critical Reynolds number, we can find out what is the value of delta, or the critical thickness of the boundary layer at that critical point. Okay. So, yes, this relation you have to remember for such cases, because here there was no prior information was given that what is the relation between the delta and the x. Okay. But for laminar flow, this is the relation that has been established and has been used very successfully for several problems. Okay. So, this is the proposed correlations. Here we have to now note this one, and we have to remember this thing for the boundary layer cases, that how it varies even for the laminar cases, because after that the turbulence begins. Fine. So, I hope second problem is also clear. Now, we move on to a bit complex problem that associates this concept of drag. So, the problem here says that consider the smooth square duct that has a dimension of 10 by 10 centimeter. The fluid is air at 20 degrees centigrade and at 1 atmosphere, flowing at a velocity of 24 meter per second. It is desired to increase the pressure drop over the 1 meter length by adding a sharp 8 millimeter long flat plates in the duct along the direction of the air flow. So, first of all, we have to estimate the pressure drop if there is no plate or there are no plates, and secondly, in order to increase that pressure drop of 100 PA, 100 Pascal, how many plates are required? Okay. So, the point is that here if we look at this, that this pressure drop when there is no plate, that means that there is a flow in a duct, okay, and the number of plates to increase the overall pressure drop by 100 Pascal. Okay. The dimensions, again take a note of this, that this is 10 centimeter by 10 centimeter cross sectional area. The fluid is air at near ambient temperature and pressure, which has a particular velocity of 24 meter per second. Okay. Inside that we have to place some 8 millimeter long flat plates along the length of the air flow in order to increase the pressure drop, because physically now you understand that when there are no plates, it will have its own pressure drop from the inlet to outlet or at a certain length. In between certain distance there will be a pressure drop per unit length or per unit yes. So, and then if we try to increase the pressure drop, we can insert some flat plates inside the that duct, and when air flows, the drag force will be there, which basically creates the pressure drop than there was normal duct. So, to begin with this problem, we require these physical properties, that is what is the density of air and the viscosity of air at that particular temperature and pressure. That can be found easily in the textbook, or this information for the time being you can understand, you can take a note that these are given. So, now in order to find out what is the overall pressure drop, which is directly linked with the flow parameter, is the Reynolds number, or how the flow pattern basically, is it laminar or is it turbulent, because based on that you can use a particular drag coefficient or the friction factor. So, for that at first we have to calculate that what is the Reynolds number of the flow, okay, for the scenario when there is no flat plate inserted. So, flow through duct, calculate Reynolds number. How do we do that? We find that, so now here we find that this is the Reynolds number. After replacing the numerics here, we see that the Reynolds number is more than whatever required to be the flow of laminar flow. Okay. So, which means the flow is turbulent. Okay. And now we go to the Moody's chart. Okay. There we can find out for this Reynolds number what would be the friction factor. Using that friction factor, we can find out what is the del P by this equation. Okay. So, here again dH is the hydraulic diameter, since this is a square duct. So, Reynolds number also has been calculated based on this hydraulic diameter. Okay. So, this value is the pressure drop when there was no plate, that is simple flow through duct. This part has nothing to do with the thing that we have seen or with the drag or the boundary layer, because this is the pure fluid mechanics problem. You can solve this. Now the point is that when the flat plates are inserted, okay, now again the drag forces are incorporated by inserting these flat plates. So we have to calculate at first what is the Reynolds number when this air is flowing through those flat plates. So for a single flat plate, we can see the Reynolds number is this value, okay, which is laminar in this case for this flat plate. And then there is a correlation for this such kind of flow, that CD is nearly 1.4 or 1.3 divided by the Reynolds number, square root of the Reynolds number. Okay. So by doing that, we find out what is the value of CD, because this CD is required to calculate the drag force on a single plate. The drag force equation, FD is CD multiplied by the half rho v square multiplied by the area on which it is acting. Now here the flat plates are in line with the airflow, so both its top and bottom, both the surfaces are exposed for this drag force to act. Therefore the total drag force on the drag force on a single plate is this value. Then the question is that we have to create an extra 100 Pascal pressure drop, okay, for the length. So that means this extra pressure drop 100 Pa, nothing but the drag force multiplied by the number of plate divided by the area of the duct, because the pressure dropped across the duct that has been asked here. So the value of single plate drag force multiplied by the number of plates divided by the area of the duct based on the hydraulic diameter, we can find out in this case what is the number of plate that is required to create that extra 100 Pascal pressure drop. I hope this is also clear. So this is again here few things, or we have now come across another parameter or another expression that we have to remember in case of the laminar flow, that the relation between the CD versus RE. This can be also acquired from the given chart or given graph that are typically given in any textbook. Okay. Now this problem says that determine the time a small spherical particle that has diameter of 10 micron and specific gravity of 1.2 would take to fall 8 feet through stagnant air. Okay. So let us say there is a very small particle of 10 micron having a specific gravity of 1.2 is falling through air. Let us say this room that has a roof from 8 feet to the ground. Okay. The properties that are required, the physical properties that are required, that are given here. So in this case, what is the time that is required? Okay. So for such problem, you can understand the point that there will be a balance between the weight, buoyancy force and the drag force at equilibrium. Okay. And this weight of the drop that is falling downward from the top of a 8 feet distance is basically balanced by the drag force and the buoyancy force. Okay. So the weight of the droplet is given by this expression, where this is the specific gravity multiplied by the density of water gives you the value of that density of that particular material multiplied by the volume and the g, which gives you the weight of that droplet. The buoyancy force that acts on this particle is given by this expressions, because it is associated with the density of the surrounding media, which is air in this case. And assuming creeping flow, because here we have mentioned this is a stagnant air. Okay. So, let us say we assume for the time being to know that what is the value of CD, the drag coefficient, to calculate the FD. We take that this is the case here. Okay. So, in this case the FD is then calculated, which is half CD rho air u square multiplied by the cross sectional area of that spherical object, okay, which here CD is again replaced by the 24 by Reynolds number, where Reynolds number is defined like this parameter. Okay. Then we can see that FD is basically, after resolving this parameter, we can see that FD is 3 pi mu u multiplied by the d, where mu is the mu of air and the d is the diameter of the spherical object. Okay. Now, this you can remember that this is the Stokes drag, the drag that has been mentioned by Stokes in creeping flow regime. The drag force acts on a spherical object. Okay. So, now if we replace these expressions, that is the drag force expression, buoyancy force expression and the weight in this overall balance, we find an expression of u, okay, which is nothing but the expression of a terminal velocity. If you remember, I mentioned that this terminal velocity is nothing but when the particle attains a constant velocity after its initial acceleration while falling through a stagnant medium. So, this is the expression of u, terminal velocity, and then after replacing these numerics that are given in the problem, we can find out that this is the value of u. So, if it is falling with this velocity from a distance of 8 feet, which is 2.44 meter, we can find out its time that is required to fall, which is around 11 minutes. And here we again cross check our assumption like we did for the boundary layer cases, that we assumed here it is a creeping flow. Reynolds number is much lower than 1, but we have to recheck our value. So, with this u we cross check, we recalculate the value of Re, and we find out that it is indeed well within the range of the creeping flow, that is well below the value 1. So, now the interesting point that you should note that this is the case that a 10 micron particle is settling in a stagnant, let us say a room where the roof is at 8 feet from the ground. So, this scenario we can relate with the paint job by spray painting. Now, there this spray of the paint can be, the paint particles can be of this size, okay, or even smaller than that. So, in that case what happens, this paints basically it will try to drop, or it will due to gravity it will fall. Okay. Now, this falling time for this, if you redo this problem for 2 micron particle, it would be around 4 to 4.5 hours. Okay. So, you can understand that if such small particles are suspended in this room, and if you inhale, okay, that can be there in your lungs for a longer time. Okay. So, such small particles creates really health hazard in such cases. Okay, that we will see in detail when we go through this particle reduction mechanisms. So the other problem, if we look at that, compare the rise velocity of an 1/8 inch diameter air bubble in water to the fall velocity of 1/8 inch of diameter of water droplet in air. So we have to compare this rise velocity when there is a air bubble in water of 1/8 inch diameter and a water droplet is falling through air of having the similar dimension or diameter. So assume in both the cases, both the droplets and the bubble behave as solid spheres. Okay. So in this case also the similar process we will take. We will try to make a balance of forces at its equilibrium. So for air bubble, when submerged in water and in equilibrium, it happens that the buoyancy force is basically drag force plus its weight. Now air bubble weight compared to the magnitude of these forces, because these forces deals with the density of the water and this is the density of the air purely. So which the density of water is much greater than density of air. Density of water is in the range of 10 to the power 3 or 1000 kg per meter cube, whereas the air in the order of 1 or 1.2 kg per meter cube. So we can safely neglect the influence of this weight of the air bubble, which means the buoyancy force and drag force are in balance in its equilibrium. And then we again, similar to that our previous thing, we replace these parameters, that this is our Fb, which is the buoyancy force acting on the this air bubble, and this is the drag force that is acting on the air bubble. Okay. So if we simplify this, we find an expression of V, okay, the velocity at which it is rising. Now this CD is unknown. Okay. So now by trial and error we have to put some V, we have to find the value of CD and find the V, and then we have to cross check our consideration by looking at the chart CD versus RE plot, whether that is consistent or not. For example, if we assume CD to be 0.5, we calculate a V 0.94 feet per second, which corresponds to Reynolds number 813. Now we go back to CD versus RE plot and then we can recheck that it's indeed this value is coming out to be, for our Reynolds number of 813, the CD is 0.5 or numerically close to 0.5. So that means our assumption of CD 0.5 fits well. So basically it involves some trial and error method to find out what is the CD and RE. So in the second case, when water droplet falls through air or in air, the similar thing happens, similar balance we have to do, but here the balance is the weight of water droplet is balanced by the drag force and the buoyancy force. Remember, the direction of drag force is in the opposite direction of the relative velocity. Okay, if you remember that, you can easily do this force balance and you can appreciate this expression. Here again, this buoyancy force, which is here, is related with the density of air and its specific gravity, which is very lower than the density of water. So we safely neglect that influence. So in this case, weight of the water droplet is basically balanced by the drag force acting on it. Okay. So we write these two expressions again, that this is the weight of the water droplet. Okay, it's basically mg, where m is basically rho multiplied by the volume, multiplied by the gravitational constant is equals to the drag force acting on it, okay, and this is the expression of the drag force. Okay. So, similarly we get an expression of V where again CD is unknown. We use the similar strategy that we apply or assume certain CD, we find out what is V, we find out what corresponds to that this V, the Reynolds number for that particular velocity, what is the Reynolds number for such problem. Again we consult CD versus RE plot to find out that whether in our assumptions were was in line or not. Okay. So, in this case we see that for CD is 0.4, this is again trial and error. After several trial and error, if we zero down to 0.4 value, we see that V is 30 feet per second, that corresponds to Reynolds number around 2000. If we consult the CD versus RE plot, we will see that for RE of 2000, CD value is indeed this 0.4. Okay. So, today what we have discussed is that couple of problems. First of all, we started with the calculation of boundary layer thickness from the leading edge to certain distance. Okay. For the laminar flow, we have to remember couple of expressions. Okay. For CD versus RE expression, we have to remember to calculate what is the drag force that comes from the expression of CD, or that includes the expression CD. And then in couple of problems we have seen the force balance while an object flowing through a media. Okay. There we have seen the balances between the buoyancy force, its weight and the drag force, and based on the relative density some expressions were neglected and we find out what is basically its falling velocity or rising velocity, and that falling or the rising velocity contain the expression of CD. That CD was unknown. So, we have assumed value of CD, we calculated the velocity, from that velocity we have calculated Reynolds number and cross check from the CD versus RE plot whether that Reynolds number indeed correspond to that CD value. Okay. So, this is the algorithm or this is the methodology you should follow to solve such problems, and in the next class we will again review the whole problem and also will solve couple of more problems. With this, thank you for your attention.